Okay, let's begin. Good morning. My name is Steve Gordon. I'm currently the chair of the CHPC Education Chapter. And today we're here to hear the presentation from Dirk Colbury on teaching parallel computing to undergraduates. So I'm going to turn it over to Dirk in a minute. If you have questions, you can put them in the chat window and we'll go over them as needed if there's anything immediate. Otherwise, we'll have a question and answer period at the end where you can either open your mic and speak or send something to the chat window. So with that, let me turn it over to Dirk. And Dirk, introduce yourself and go ahead, please.
Hi, everybody. I'm Dirk Colbury. I'm at Michigan State University. I'm in a department called Computational Math, Science, and Engineering. And today I'm going to be talking about my course called CMSE 401, Methods in Parallel Programming. It's an undergraduate course. Can everyone see my slides? Okay, excellent. So let me tell you a little bit about our department. We're a new department. We were formed in 2015 as a way to be kind of a mesh, automatic slides, kind of a mesh between the College of National Science and the College of Engineering. We're kind of in both colleges, and we're computational math, science, and engineering, so we're everything. We currently have on the order of 32 faculty in the department, and so we've had a rapid growth rate. We've had a graduate degree. But the idea behind the department is the intersection between engineering and physical applications in engineering and natural science and computer science and applied mathematical analysis, kind of the joint of all three. Really, how we use computers to do science and engineering is kind of the catchphrase we use. The CMSE department, as we're new, we're building up very quickly. So I was hired mostly to develop new curriculum for the department. We have a couple graduate programs, and we're just starting this fall right now an undergraduate program in scientific data analysis. And so these are all new programs, and they need new classes, which is where I step in and develop a class. I'm also the new graduate recruitment director. So I'm going to do my plug right here. If you have outstanding undergraduate students that want to go to an outstanding department, send them my way. And if you do, I will graduate them and send either our undergraduates your way or send you awesome postdocs and faculty and such. Let's make we're new, so we don't have a lot of established relationships. We have to build them from scratch. All right, done with the advertisement. So today is, I'm going to talk about 401, which is a senior level undergraduate question. Oh, I thought I heard someone.
Okay.
It's a senior level undergraduate course in parallel programming. This was a completely new prep. I had to start designing it from scratch. Actually, it says, with the help of this group last year, which is sort of true. I actually gave this presentation as a part of a SHODOR workshop that I can see Dave was on and helped me quite a bit. He's waving now. He helped me quite a bit get started. This workshop was great. If you have questions about it, they held it again this year, and I couldn't attend. But I think they're planning to hold it again. And the idea of this workshop was to get people developing courses in high-performance computing together and share curriculum and get together. It was pretty neat. So I needed a format. So my job is to develop the curriculum and teach it the first few times and then pass it off to our junior faculty who do not necessarily have a lot of experience developing new courses and may not be familiar with modern pedagogy and how to teach effectively. And so the idea is, can I generate some curricula that I can easily pass on to the other faculty? So with that being said, we had a 15-week semester, and I only had 18 students the first time. We expect that number to go up now that we have the new undergraduate degree in data science, but as a first time, it was reasonable. So if I made any mistakes, I could catch. It's easy to catch students up. We did have one graduate student. We actually had another parallel course that started in computer science that was completely an unintentional conflict. They had a lot more students because they have a more established program, but it was really meant for computer science, so it was heavy in theory and slightly different focus. But our feedback was pretty positive. So I have a tiny URL here. If someone wants to take a few moments and type that into the chat window for me, that would be really helpful. It just gives you an idea of what we did over the semester. What did I want to say? I need to see my notes. The main topics of the course, loosely talked, we got students into how to navigate a shared computing system, which was how to use SSH and Bash. We talked about single processor optimization in C and C++, how to make your serial code go faster. And then we moved into shared memory parallelization. Then we did accelerator, basically CUDA programming, and we ended with MPI. And the idea behind that ordering was we wanted to give the most impact to the students as early as possible, and they're more likely to be using serial code, they're more likely to be using OpenMP, and now that GPUs are pretty much everywhere, they're much more likely to need to be learning CUDA programming instead of MPI. I think that was a Dave thing, by the way. It really worked well. So my main goal for the course was to have every student that comes out of 401 basically able to walk into any lab on campus and help running experience on our local HPC or Exceed resources or something like that. So they needed to know how to log on, get experiments running, benchmark, and then get them going faster using parallel methods. We didn't dive necessarily too deep into the minutia of the different approaches, but I wanted to give the students enough information so that they could take a program written in those parallel methods, get them to compile and run on the HPC, benchmark them, and maybe modify them or update them. That was the general idea. I wanted everyone to be able to do that. Just for fun, I show you how I organize my curriculum development. I have this on my wall, which is painter's tape in my office. Each box, I don't know if you can see my mouse pointer, but each box represents a week. So this is the first week, this is the second week, this is the third week, and we have 15 weeks total. And we met 3 times a week, and we would learn about parallel programming. But every time I got ideas, I would write them down on a note, a sticky note, put them up on my wall, and I could move them around and get ideas on how to relate everything to my learning goals to the class and make sure the ordering and the pacing worked out well. This method was taught to me by a colleague named Brian O'Shea, and I love it. I use it for all my development of new courses. So the format of the class is in a flipped classroom, which means I try really hard to have students have hands-on keyboards during class, where they're logging on and doing things and practicing in class. And we do this by giving them pre-class assignments that include videos and small little reading snippets or examples that they can run and try out before class, so that when they come to class, they're prepared, and then we can actually do some real hands-on keyboard activities, and they can help the neighbors, and it becomes a very interactive classroom. We also have homeworks that are due every other week. These are meant to get into a little bit more detail about something that we normally wouldn't be able to cover in one class period. It really makes the students dive in and try to solve a problem in more detail. I also do exams. My exams are famously hard. All the undergraduates know that if you take one of my courses, my exams are hard, but I actually get very positive feedback. They're challenging and interesting. I make them all open network exams. I make them program on their exams. The only real restriction I have is they can't communicate with peers during the exam. They can Google anything they want or look at any examples that they have, but they really shouldn't be talking to someone else or communicating through the internet with someone else. And then finally, we end the whole semester with a student project that they pick out and present to their peers at the end of the semester. Actually, they present a couple times during the semester so that everybody can learn from each other. I write up all my assignments using Jupyter Notebooks. Why use Jupyter Notebooks, you ask? Isn't that just Python? And what does Python have to do with high performance computing? We actually use Jupyter Notebooks for all our classes, not as an IDE. It is not a very good IDE. It is a communication tool. It is like the intersection between a textbook, a web page, a Word document, a LaTeX document, and runnable code. And so by having that intersection although they become an excellent way to communicate, and since teaching is all about communication between the instructor and the student and the instructor, it becomes an ideal tool for communicating with our students. So now I'm going to switch over and show you some examples. By the way, this is really weird to talk to you all because I don't see anybody, so I'm just talking to my computer. So if you have questions, feel free to ask. Internet, okay, that didn't work. There we go. So this is what Jupyter looks like. We provide, we help the students install Jupyter using Anaconda on their local machine. But we also have a Jupyter Hub server running in our engineering building. And the server just gives a common platform so that if something's broken on a student's laptop, to a shared resource. And our shared resource happens to also have GPUs, which makes the CUDA part really nice to program and test out. And so this is what the interface looks like when the students come in. They download these files. They're called IPython notebook files. And here's what a typical pre-class assignment might look like. You have, let's see, should I make that bigger? Can you see that? Now you can't.
Yeah, we could see it, but
there we go.
Okay.
It was just a little blocked for me. I'm going to move my camera slightly. So the pre-class assignments, this would be sent to the students as a notebook, and they would see it just like this. They could double-click on a cell and edit it. These use markdown cells to get the text looking nice. But I'll send this. It gives a brief little outline what they're supposed to do today. It has an embedded video. This video, for example, tells them how to log on to our local HPC using SSH and X11. So they have this video. They can watch it. I don't know. I try to make my videos about 5 minutes long, so we don't have to watch this, but I'm curious to see. No, we don't care about that. Yeah, this video is almost 6 minutes long, and it just gives an introduction to how to log on to the HPC. And then we talk about using Git, because we use Git for a lot of their projects and giving them content. In this particular pre-class, we talked about project proposals. So they had to type up some ideas they had for projects so we could discuss them in class. And then all of our pre-classes have this assignment wrap-up where we ask some questions. These are very helpful in all of our teaching. We ask things like, what have you heard about that you're hoping to learn more about? Do you have any further questions or comments about this mirror? Anything else that is going on in class? We specifically ask every day before class comments for questions from the students. And then what they do is they fill out this Google form and they answer the questions. And then before lecture starts, or before class starts, because it's not really lecture, I review all of their questions and then I make a few slides. Then that's the first thing I do in class, is I present them with their questions and hopefully answers to their questions. Students learn very quickly that I will answer their questions if they put them in this form, and it becomes very dynamic in class. It makes a really good feedback mechanism to catch topics that they really are curious about or didn't fully understand, and I use it for all of our teaching, and I highly recommend it. So we can have the Google form built right into the Jupyter Notebook, which they can fill out within the Jupyter Notebook. And then at the end of every notebook, I always put links to the main class links, like syllabus and preliminary schedule and stuff like that. So that's what a normal pre-class would look like for one of our courses. And then in class, they get a Jupyter Notebook. And so they would show up in class. This would be on our content management system that we use for all of our classes. So they would just download the notebook. and then upload it. And as students are showing up, they start the notebook and they review the tasks that we're going to do today. I always put an agenda in with an estimated time of how long things will take. And then we go through the notebook. It gives the opportunity to students to skip ahead and try out the example. This particular notebook is a CUDA example. And so you can see that I'm just using, this is just your CUDA file that you would write normally in whatever editor you want. You can edit it right here inside the notebook and execute it. And then the next Jupyter command just runs your compile command that you would normally run on the command line. I make them do it on the command line as well, but this gives them a list and step-by-step instructions on how to, what they need to do. So they edit the file, they run the compiler, and then they can run the actual example, and it shows whatever output it's going to show. I also can tag and put cells in my notebooks with this hashtag answer keyword. And I have a little filter that we wrote that just gets rid of all the cells that have the word answer in it. And so we can have one document that is the instructor document with all the answers in it. And that generates the document we send to the students. Not only do I put answers in here, but I sometimes put notes to the other faculty or future me who might teach this class again, and remind the future person what went well, what didn't. And so that those notes are right in the notebooks when I'm planning to use them, and can review them and update the notebook the next time I teach the course. And so, yeah, here's another example. So that's an in-class assignment that we might do. And then here's a typical homework where we did some image analysis. One of the things where the Jupyter Notebooks come in neat, I think this was CUDA. This might not have been CUDA. This just might have been OpenMP. But we did some windowing methods, and they had to do some image analysis, write some code, and check it in. But what's neat is then I can load their images inside the notebook itself and view them. Sometimes that can be hard on the HPC, but in the notebooks, it's really easy. And so that's how we use Jupyter in class. I really like it. It's a great way to organize my lesson plan, my objectives, how everything links to my learning goals, notes to the instructors, answer key, rubric, all can go into one document, so I'm not fishing around for everything. I've been doing this method of course design since 2015, and we really like this method. It really makes communication between the instructors really nice. I don't know if it's for everybody, but it really works for us. Let's see, let's go back to my slides. Some fun activities we did. We used the SHODOR BCCD that I think Dave helped develop. It's a really great little live image that we loaded into VMs, virtual machines, on some laptops. And then we connected them through just a wired hub. So we had about, I think, only 6 laptops, but it was really neat. I made the students plug everything in and run the VM. They had to install the VM software, get it running, connect all the computers together using BCCD, which makes it really nice. And then we had a mini little HPC that we could run some examples that come with a BCCD. There was a particle example using, n-body example using Galaxy simulations, and there is a pandemic model, really great visual models that we got to run in class and benchmark and graph how fast things were right there in class. We also did a tour of our local HPC system. And one of my activities that I really like is I made them do matrix algebra, where each one of them is a CPU and they get a little bit of board space for RAM. And they had to figure out an efficient way to do a large matrix algebra multiply by talking to each other through notes. It was really fun. So that's just activities that we do in class. I try to keep them engaged. They are undergraduates after all. We also do some really engaging homework examples that get to dive a little deeper into. I showed you the example for the image analysis, but I also do a 2D wave equation, a 1D wave equation, an agent-based model of a rumor mill. It's called a rumor mill model that is a lot of fun and visual. And we also do flat up things like data analysis of genomics and stuff right there on the HPC. So those are the types of things we would do for homeworks. A lot of them is just taking code that already exists, benchmarking it. That was kind of the first few homeworks. And then we would take code that already exists, benchmark it, and modify it to make it go faster. And then towards the end, they were writing some of their own code. And so it really worked out well. Also, I want to point out the very first homework was write a 1D wave equation in your favorite programming language. And then we compared it to C, C++, and how fast it could go. That was totally Dave Joyner's idea, and it worked wonderfully. He helped me with some of the code. It really set the pace for the rest of the semester, especially when we ended up going to the 2D wave equation. The students were really ready for it. So that was kind of neat. The projects, well, I tried not to make it all about the coding because I wanted skills that they actually might use in a lab as undergraduates. And what are those types of skills? So I wanted them in a stage 1 of the project, they had to identify an existing piece of software used in research. Preferably research they were engaged in, but not all undergraduates have research projects. But they have usually their area of interest. They might be physics students, they might be engineering students or whatever. And so then I had to have them as their first project download and install the software on the HPC at our local university. So they had to, we taught them a lot on how to do software install. And then they had to make an example and get it to run on the HPC, whatever the example might be for whatever piece of software they're using. This software didn't have to be parallel. It could just be a piece of software used in an area of research, something that could be used on our local HPC. And so I helped them find what that software might be, but they came up with great little stage 1 projects. And then they exchanged instructions and examples with their peers, and their peers had to try to install the software using the instructions and get the example working. Didn't always work well, but it was a really good exercise on how to write good documentation. And then stage 2 was they had to, and that write is spelled wrong, I just noticed that. Write, as in write, or modify an existing code to be parallel, or take a code that's already parallel and benchmark it by changing the parallel and finding the optimal way to run the code. Really, I wanted them to modify something or take something that wasn't parallel, turn it into parallel, or take it something that's running in parallel and figure out how to make it run most efficiently on the HPC. And they had to run benchmarks and demonstrate that they figured out what was the best way to run the code on the system. And that was their secondary code. So it involved programming, but not everybody's a great programmer in this class. And I still wanted it to be challenging and useful and bring it back to their home labs. And so that's the projects we came with. Here are just examples of titles of projects that students did. And you can tell that there was a wide variety. We had students from many different majors participating in the course. We had a couple people really interested in TensorFlow, so we got that all figured out and running. Someone wrote an entire stock market simulator from scratch using Charm++. That was an interesting project. So those are the types of things we had them do. And what was neat about having the projects and having multiple check-ins throughout the semester is a student would be working on their project, but they would also be learning about everybody else's projects that were going on. And so they got to see how people tackled solving the problem from different ways. So I have a bunch of Jupyter Notebooks. I'm happy to share them. I'm not really ready to make them public yet, but if you want to see them, I'm happy. Send me an email. I'll tar them up, send them back to you. But if you have some cool examples, I'd love to share them with me. I'm happy to, always looking for new ideas, and I will happily give credit where credit is due. Hopefully I gave David enough credit because he was awesome in helping me get started on this. And I made this presentation intentionally quick, hoping that some of you would ask me a lot of questions so I didn't have to prepare more slides. Any questions?
So let's open up for questions. You can either put something in the chat window or you can unmute and ask your question of Dirk.
Weird.
What is the process to eventually making the videos public?
The videos, yeah, I could make them public. Right now they're private, meaning they're posted on YouTube under a private channel, and you have to have the URL. So any of the Jupyter Notebooks I send you will have the link in it. Our university is very hinky about making things publicly Google searchable without being fully authorized by our accessibility group. Curious, but we have, and I don't want to say anything illegal, so I don't know the lawyers in the room, but we have two layers that we consider. Our first and primary goal is to make sure things are accessible for our students in our courses. And so we do our best to accommodate our students. And so by making my notebooks not public, I'm really writing them for my students, and then my students' needs can be met based on whatever needs they have. If we make them public, we have to make them accessible to anybody that might view them. And that's a lawyery issue that we have. And I actually agree, is I don't want to post things that aren't fully accessible out there. But fully accessible is a hard standard, especially when you're teaching coding. I've also been working really hard to make Jupyter more accessible as a tool, and it's somewhat, but it's not accessible.
Dave asked, is interested in how you hooked up the Jupyter Notebooks to your hardware and got shell access.
So I'll show you. Hey, puppy. So first off, this is the Jupyter Notebooks running on a server. I think it has 24 cores, 3 GPUs, 256 gigs of RAM, something like that. A pretty hefty server, but still just a tiny server that's out there. It's more than enough for 18 students to drop on and use the GPUs for class. We don't have we haven't had any collisions. I was curious to see if we would, but we didn't seem to. All the examples we use are so friggin' fast that the built-in schedulers and stuff seem to work fine. At least we didn't notice any noticeable issues. But when we log onto the HPC, Jupyter itself, I can go up to new and I can say terminal, and I can actually connect to our local HPC. So I'll just SSH. And I think I hit a bad key, so I don't know if that's going to work. I did. So I can log into our local HPC. Since this works really well, there's no login required. It does not use X11, so I can't run anything that uses X11, but I don't really use it a lot in class. The video I showed you did use it, but that was also meant to be a general video in case other people wanted to use it for local access. But this is primarily the way we connected to our local HPC. We also connected to Exceed. If they allow SSH access, you can do it fine from this as well. So that's built right into our Jupyter Hub. It's a normal part of Jupyter. It also gave me a really nice interface even when we didn't log in. I taught a lot of bash scripting and just how Slurm would work and stuff like that. And so a lot of just the bash examples I could do from this local bash script. And when they install Anaconda on their local machine, they get this as well, which is really nice.
Next question is, do you use auto grading for any of the notebooks, or you do it manually?
I love the idea of auto grading because, you know, grading takes a lot of time, but it goes against a lot of our pedagogy, at least the current auto graders. I don't care if students memorize crap. And if you can auto grade, and it usually has to be short answers that match something. And it's really hard to get set up to work right and still, in my opinion, have meaningful questions. Let me show you. See, I should have an exam question here. Come on. Let's see, where are my exams? Did I miss them? Final exam, here we go. So here's an example of an exam, and it's very grading intensive, I know that, but also I think it's also challenging and gives the students a lot of freedom to get partial credit and get ideas. So I do 4 questions, each are 25 points, and then each question is broken down into sub-questions, but I try really hard to make the sub-questions not dependent on each other, so that answering one question does not depend on answering a previous question as best I can. And so Here we talk about how makefiles work. So we did cover makefiles in class, but the point of this little was to talk about this option they've never seen before, which was the way to run makefiles using shared memory parallelization. And they had to ask some questions and figure things out by Googling and see if they could get it to work. And it really was a question to see if they understood how shared memory parallelization might work and see if they could figure out how to do makefiles. So that's an example of a question. Oh, and measure speed up and stuff like that. This talks about distributed memory, an example. I always try to put a picture in just to get a little bit of motivating. Here's a matrix multiply example. A lot of these they haven't seen before. I always try to show them something they haven't seen, and then they have to apply what they're supposed to be learning, which is concepts on parallelization, to the class. So I know that's not enough time for you all to read these because that wasn't an intention. Here's a fourth question about CUDA texture memory. We never covered that. That was a detailed question in the class that I never covered. But in this exam question, I asked them what it is, and they had to go look it up and see if they could figure out and read through this code and figure out what it's doing. And that's pretty neat. If they can do these types of questions, they're very difficult, but it really demonstrates understanding of our main learning goals, which is to be self-learners, not just to regurgitate syntax. And because of all of that, I haven't been able to figure out how to do auto-grading of my style of questions. I think people love their auto-graders, that's great, but I think it detracts, at least the way I'm teaching, from some of the pedagogy. And so we haven't found a good way to do it well.
Another question is, have you considered doing this for having remote students, and what might be some of the challenges of doing that?
Because we do videos and they do the pre-class assignments in videos, all of our administrators say, hey, you're halfway to we're halfway to a fully online classroom. No, and then we always push back because the real learning happens in class with the students' interactions with the instructor and each other. That is where the real interactions go. I think this could be translated to an online course, and we want to study that, but we don't also want to take away from the class. I think to do it, we have to somehow find a way to do effective group work where students can look over each other's shoulders effectively online. And I think Zoom could do it, but it would take a little bit of a learning curve for our students as well to get up to that, as well as the instructors. I'm worried about it. I like the idea of it, but I really worry that it takes away from the highest impact part of the learning, which is the in-classroom stuff.
Aaron asked, it says it looks like they had to provide an email when they gave a question. Do they have a way to give anonymous feedback?
There are other ways we get anonymous feedback. I do not look at their emails unless there's a concern that I need to address. So I tell them it's not anonymous, but I also tell them I don't look. So that kind of stems the ability to ask questions and feel a little bit safe, but also not be a jerk. And we have other fully anonymous feedback functions specifically so that they can say anything they want. We do that in the middle of the semester and at the end. But a lot of times I need to talk to students outside of class, and I want them to feel comfortable just always asking their questions in the same format. I could go also anonymous, but filling out the form as well is how they get credit for participation. We don't grade the pre-classes.
Is your approach to teaching gaining momentum across the department or even broader at the university?
So definitely across the department, a little bit across the university. I mean, I actually modeled this course after our intro and advanced modeling courses. So we have an intro to computational modeling, which we call 201, completely done in this format. Then we have 202, which is tools for computational modeling, basically software development tools. And that one is also done in this format. And I've been teaching those courses for a while. We also have a bunch of graduate courses done in this format. What's nice about having a common format like this is that we can help the junior faculty who really should be focusing on tenure to focus a little less on, because some of them were quite stressed about teaching, try to give them support that they need, and so that give them some familiarity with a format so they can walk into a course that maybe they haven't seen before, but still comfortably can walk in and hopefully teach it. I really like the format. We've now seen it in physics classes being taught and math classes being taught, and I think we're going to see it now in some engineering courses as well. And so the feedback from the students is very positive. I also think based on pre and post surveys that they're actually learning stuff. We don't have a longitudinal study yet, but we are working in verifying that they're learning things in these courses. We have a few papers out on that.
Cool. There's one question that says, have you tried using the desk library in this notebook? They're curious to know how it maps to the cores on the cluster through notebook.
Nope.
Okay.
I don't even know what that is.
Yeah,
honestly, we're not running the notebooks on the cluster. I'm making them SSH in and run things on the cluster. The notebook is really just a communication between me and the students. Because when they leave, chances are they're not going to go to a lab that is running notebooks on the cluster. Most labs are still using standard CLI interface.
Right. All right, are there any other final questions? Can you share a lesson plan for the matrix multiplication activity where they act out the algorithm?
Yeah, except that one's my weakest one because I do it from memory. I also do it in my linear algebra class when I introduce parallel concepts. So it's a twofer. I can introduce matrix multiply in linear algebra to do parallel, and I can do linear algebra in parallel. So let's see. But yeah, if you want to send me an email, I'll definitely send you that. I don't remember what day I did it on, and it's not part of the title, so I'd have to go find which day it is. I actually have I could grep it or do my little search feature. But yeah, that's a good question. I don't have it in front. Basically, I just put a big matrix on the board, put another big matrix. I try to scale it so that there's, if there's 16 people in the class, I do a 4x4 matrix. If there's more, I do more. And then I give them a little square on the blackboard and I say, okay, go calculate your row and column calculation and then figure out how you're going to put it together. And we do it a couple different ways, and they start to see what happens when you try to share memory or you have independent memory and stuff like that. It's kind of fun. But I'm happy to share.
There's another question on where to find documentation and how to use Jupyter for communication in the way you do. Do you have is there a resource that someone could use if they're starting to use this approach?
That's a good question. Oh my gosh, Jupyter is blowing up. If you want to use it, it's easy to get started. There are a billion examples on GitHub right now. I'm happy to go look for a few and send it. I know a few people have written books about Jupyter. I haven't really used them that much because we started using Jupyter about the time everybody else was starting using Jupyter, and so I don't think we're doing anything special. Well, I'm doing something special, but I don't think in general we're using notebooks in a special way or anything like that. So I'd be happy to share mine, but I could also maybe do a little research and help you find something that might be a good resource. I mean, it's free. That's the other reason to use it. It's just an open source project that comes with Anaconda.
You had several compliments on your on your presentation, and then let me add mine. That was a really excellent presentation. I will, for those who want to review what's gone on, we will be posting this program to our SIG-HPC Education YouTube channel sometime in the next couple of days. So that will have Dirk's everything Dirk presented, and then you can get in touch with him in addition if you want to interact on any of the materials. So Dirk, thank you again for your presentation, and thank everybody for joining us today, and everyone have a good rest of the day.
Thanks, everyone.
Bye-bye, everybody.